Hi folks, welcome to the last wee video of our circles topic. This is lesson 7 and what we're looking at this time is circle interactions and the ways in which circles can interact with one another, and really we're looking at kind of 4 cases. As I go through these, again you might want to pause the video and just copy the diagrams into your notes jotter, and then listen to me kind of talk you through each of the examples so you understand what it is we're actually comparing in terms of how these circles meet. Let me just go through the 4 and then I'll come back to them and kind of explain how we can prove which of these scenarios we're in. So 4 ways that circles can interact. Either they don't meet, okay, and these are really similar to how lines and circles interact or how lines and curves interact, particularly in terms of quadratics. So they either don't meet at all, they can intersect at 2 points, or we can have a scenario where where the circles are like tangential to each other, where they just touch one another. But we've got 2 kind of separate versions of that same idea. We've got where one of the circles is on the inside, and we've got the other one where it's on the outside. So in example 3 here, we can see we've got one circle outside the other, and they touch externally, and then we've got the other one where the small circle exists within the bigger circle, and we call that touching internally. Okay, so we're going to go back and look at all 4 examples and look at the criteria that we can analyse mathematically to decide, without having to sketch these accurately, which of these kind of scenarios we exist in. Okay, so example 1, where the circles don't meet at all. And the way that we're going to analyse this for all 4 scenarios is we're first of all going to work out the distance between the centres of the circle. Yeah, so if you remember, finding the centre of a circle is something that we can do from its equation, and is often information that we'll have. So I can go ahead and find the length of the red line here, which represents the distance between their centres. You can use the distance formula for that, or what we've been doing in class is just trying to take an approach where we kind of just use Pythagoras and sketch this out as a wee right-angled triangle. So we're going to be looking for the distance between their centres. And then the second piece of information, again, it's the main other piece of information that we get from the equation, is the length of the radius for each circle. You can see I've got one in blue here and I've got one in green. For all the diagrams, R1 is a bigger circle than R2, but that only plays a part in the 4th and final example, where it's important that you consider the smaller circle against the bigger circle. So what we're looking for in this first scenario is we've got this distance, that these 2 circles are apart. Let's just, for the sake of applying some numbers to this, say that they're 10 units apart. So the distance is 10 units. Then if the radius, let's call R1 5 units and R2 3 units, then there's no way that these circles can meet, because their radii aren't big enough to close the gap between them. In fact, you could tell me even more information about this. You could tell me that, in fact, at their closest point, the circles are 2 units apart from one another. Because if you've got a space of 10 units to close, and the first circle, the larger circle, only closes in 5 of those units, and the other one 3 from the other direction, we still have a gap of 2 between them. Mathematically, we write that as a little statement like this one down at the bottom here. If the distance is greater than the sum of the radii, then the circles can't meet. The distance between them is too big for the radii to close. Okay, so you can see from the 2 statements on the screen, and in fact from the 2 statements on the next screen as well, that it's always a comparison between the distance between the centres and some interaction between the radii of the circles. Okay, so if they don't meet, the distance is greater than the sum of the 2 radii. If they do meet, and again, let's take this distance here. Let's keep the radii the same size, so we'll call radius 1 5 and radius 2 3. Then the distance between the centres, you can see, is much closer this time. Let's see, it was only 6 units. So the circles, if they had no radius, would be 6 units apart, but then the bigger radius closes in by 5 units towards the other one, and the smaller one moves in the direction towards the bigger one of 3 units, then they overlap by a value of 2 units this time. Yeah, so they're not apart by 2 units, they actually overlap by these 2 units this time. Okay, and the way that we're going to articulate that mathematically is if the distance between the centres is smaller than the sum of the radii, then the radii of the circles are big enough to close that space between the centres. Okay, so we've got greater than. If the distance is greater than the sum of the radii, they don't meet. If the distance is less than the sum of the radii, then they intersect at 2 points. Okay, the last two look at what happens when we have some kind of equality, and this communicates really nicely with how we've used the discriminant in both the quadratics topic and in circles, where when we've got equality, there tends to be 1 point of contact. Okay, and again, what we could do is we could say, okay, this time the bigger radius is 5, the smaller radius is 3 still, and the distance between them is 8. Yeah, so if you imagine the distance between these two circles is 8 units, and the radius of circle 1 comes 5 units in that direction, and the radius of circle 2 comes 3 units in that direction, then you can see that they meet perfectly at this point of contact here. So that happens if we add the radii, and so for all 3 examples so far we've been adding them. So we are adding the radii, and if they are less than the distance, they don't meet. Greater than the distance, they overlap and they have 2 points of intersection. But if we have this equality where the sum of the radii is equal to the distance between the centres, then they touch externally. And the last one, I suppose, the one that kind of stands alone, is it's the only one where we are actually subtracting the radii, and this is just to check if perhaps one of the circles exists within the other one. Now, of course, that circle could exist within that bigger circle and actually not meet. Yeah, you can imagine the circle could exist in like this space here and it wouldn't actually touch. So again, we're actually getting this equality going on, that's the important factor for them touching. What we have is we've got the larger radii, and we have to subtract the smaller one from it. You can see the problem if we subtract the bigger one from the smaller one, we end up with a negative, and it's really hard to kind of sense make of that result. Okay, so again, if I just stick with what we've been talking about, we've got a larger radius of 5, a smaller radius of 3, and then the distance between the centres would be 2 in that case. And you know, you can see hopefully from that diagram that the difference in those radii is equal to the difference between their centres. Yeah, if I put the centre of the smaller circle there and the centre of the bigger circle there, again, it's that distance is equated to perfectly the big radius subtract the small radius. Okay, so we're just going to look at a couple of examples using these properties. This is regarded as quite a difficult idea by the SQA, but it's certainly something I think hopefully if you have a wee look at these diagrams as you try the questions, you'll come to grips with really quickly, and hopefully something that you guys will be able to answer in due course. So here is example 1. We have been given 2 circles. We'll be able to tell which one's bigger and which one's smaller once we start to explore them a little bit. The questions often have a lead-in like this, where it's like write down the centres and radii of C1 and C2. And even if it didn't, we've discussed whenever you get an equation of a circle, these are the 2 things you're going to write down straight away. So we've got C1 is our first circle and C2 is our second circle. Typically, you'll get given them in different forms because they assess different skills and different ways of interpreting the equation. So if we have a wee look at C1 first, so I'm going to write down the centre of C1 as a coordinate, and I'm going to write down the radius of circle 1 just as a value in terms of units. Okay, this is the easier of the 2 to interpret. So remember, we've just got a sign change from the 2 values that exist within those brackets. So the centre is -5 and 6. And then the radius, remember the radius is over here, but that's the radius squared at that point. And so the radius for this one is just going to be 3 units. Okay. And then on to circle 2. So again, to get the centre of it, a little bit trickier. I'm going to do a little bit of working at the side for this. So we've practiced this in the previous video. We're going to start with 2g equal to -6. And actually you'll notice that there's something missing, right? We don't have a y term in there. And we saw this in class the other day. We've got that 2f then is equal to 0. This gives me g is equal to -3, f is equal to 0, and remember your centre is -g, -f. So our centre in this case, sign change in both of these, can't sign change 0, so it's still just 0. So we've got a centre at 3, 0, and the radius we're going to work out, but again, slightly more complicated. So the radius is equal to the square root of g squared plus f squared minus c. This formula is on your formula sheet, yeah, so you get given this, you get given what the centre looks like, you get given your general equation and how to get g and f, or where 2g and 2f exist. So not a huge amount of pressure to try and remember all of these. The important thing is about utilising these effectively from the formula sheet. Okay. Let's substitute in here then. So we've got g, so that's -3 squared plus 0 squared, and it's subtract, and have a wee look up here. Here's my c value, and it's -16. I'm actually going to go straight to then add 16 because we're subtracting -16. And what we get out of this is 9 plus 16, so we end up with root 25, or we have a radius of 5 units for this one. Okay. And that's part A done. That was all we're asked to do. Find the centres, find the radii of C1 and C2 respectively. So job done. Okay, show that C1 and C2 do not intersect. So let's just take a quick look back. They don't intersect, so we're expecting to get something like this, where the distance between their centres is greater than the sum of the radii R1 and R2. So we need to know two things. We need to know what R1 and R2 is equal to, and again, we can actually write down that fairly quickly. So R1 plus R2 is equal to 8 units. So we've got that written down. And then the other thing we need to know is we need to know the distance between the centres. So we've got the two centres here and here. I'm going to find the distance between them. Now remember, we've been doing this as just a bit of Pythagoras. So I'm just going to plot these 2 points. Again, in no kind of thoughtful way. I'm just going to plot 2 points, join them with a line, and essentially I'm trying to work out the length of this line. Let's call it D. And to do that, I'm going to create a little right angled triangle. So this point here is the point 3, 0. This point here is the point -5 and 6. Okay, so in terms of my x movement, I've gone from -5 to 3, which is 8 units long. And then on the vertical axis, I have travelled from 6 to 0. So again, 6 units here. Okay. So I am going to now do a bit of Pythagoras for those. So d squared is equal to 8 squared plus 6 squared. D squared is equal to 64 plus 36. So d squared is 100. And therefore d is 10 units. Okay. So we now know two really important pieces of information. We know the distance between them, and we know the sum of the radii, and we can just write a little statement using that criteria that it gave you previously, which is as d is greater than, so the distance between them is too big, even if I add both the radii together, it's not big enough to close the distance. So as d is greater than R1 plus R2, the circles do not intersect. Okay, and that's our solution to that one. So it's really similar little statement as if you'd used the discriminant. Yeah, as b squared minus 4ac is greater than 0, you know, there are two real and distinct roots, that kind of thing. So it's that kind of statement that you're creating there. Okay, example 2, slightly different, but same idea underneath. So circle P has an equation x squared plus y squared minus 8x minus 10y plus 9. And circle Q, so they've not given us two equations this time, they've actually just given us all the information for circle Q. So I'm just going to highlight that information so we can come back to it. So a centre, -2, -1, and a radius of 2, root 2. And that is for circle Q, yeah. I might even write it as circle Q, something like that. Okay. Show that the radius of circle P is 4 root 2. Now, I can see where this question is going. Show that these circles touch. But anytime I get given an equation, I'm going to write down two things. So yes, it asks me for the radius, but I'm also going to write down the centre whilst I'm at it. So I'm going to write down the centre of P. And again, I'm going to need some information for that. So I've got that 2g is equal to -8 and 2f is equal to -10. Therefore, g is equal to -4 and f is equal to -5. And that's going to give me a centre of 4, 5. So I wasn't asked for the centre, but I had to find g and f to find the radius anyway. So why would I not just go ahead and find the centre too? Because I know I'm going to need it in just a wee minute. The radius then, which I'll store over here, so that the radius of P, I'm going to find over on the right hand side here, but I'll store the information back on the left there. So we've got that the radius is equal to the square root of g squared plus f squared, again minus c. So the radius is equal to the square root of, we've got g and f just sitting there. Again, you can almost use these devoid of sign. This time, c is positive, so I am actually going to be subtracting 9 from this. What's this give me? This gives me 16 plus 25 minus 9. Because this is a show that, I'm going to do a bit more working than perhaps I would do if I was just trying to get to the answer here. I don't want to skip any line in case it's a line that the SQ have deemed important. So we've got 41 minus 9, which is root 32. That's not what I have to show either, but what we've got here, we've got a surd, and we know that we can simplify these. So that's going to be equal to root 4 multiplied by, in fact, though, I've got a bigger square I can take out of that. I'm going to take out root 16 multiplied by root 2, and that's where I'm going to get this 4 root 2 from. Okay, so there's my radius over here, 4 root 2. Okay, so what I've got now is I've got the centre of P and the radius of P, the centre of Q and the radius of Q. And now we're going to go ahead onto part B and show that the circles touch. So again, just to flick back to what happens when they could touch in two ways. I don't think it says that one exists out with the other. So it could be either of these scenarios. I'm going to try adding the radii first and see if that's equal to the distance. If it is, great, we've found the answer. If not, I'm going to subtract the 2 radii and see if that's equal to the distance. If neither of these statements are true, then the circles don't touch. But given that it says show that they do touch, I'm expecting one of those to work. Okay, let's find the distance between the centres again. So we've got 2 points. We've got the centre of one of them, 4, 5, and the centre of the other, -2, -1. And again, I find this much easier than the distance formula. We're just going to create a little right angled triangle and consider the change in x and y. So we've gone from 4 to -2. Now this is completely the wrong direction for a Cartesian diagram, but it doesn't matter. We're just going to write that that's 6 units devoid of direction because we're only interested in the length, like the magnitude of that line, not its direction. And then we've got 5 to -1, which is also 6. Okay, we're going to find d then. So d squared is equal to 6 squared plus 6 squared. So d squared is equal to, and that's 36 plus 36. So d squared equals 72. D equals the square root of 72. Now, if you have a quick look, we've got this one in terms of root 2 and this one in terms of root 2. I'm going to try and get this in terms of root 2 so that I can equate them. And so if I just simplify this as a surd, we've got root 36 multiplied by root 2, which is 6 root 2. And I can see really quickly now that it looks like the sum of these 2 radii is going to give me this distance here. So I've got to write down an additional wee statement here, which is that the radius of P plus the radius of Q is equal to 4 root 2 plus 2 root 2, which is 6 root 2. And then I'm totally out of space here, so I'm actually going to go up and just write my answer up the top here. But it's the same kind of statement as before. So as d is equal to the radius of P plus the radius of Q, the circles touch. We can give them a bit more information. They don't ask how they touch, but we can say that the circles touch externally. Okay, I'll just highlight that so you know that's where our solution is. So got this idea, and that's based on D being equal to this, and the sum of the radii being equal to that. Okay, that's almost like kind of converse of Pythagoras approach, you know, where you consider the two things separately and then you equate them afterwards in a restatement. All right. Only a couple of questions to try on that, not particularly common, but you'll find them exercise 12H, question 12 and 15. Again, that page number is accurate for the first edition book. The second edition book's a little bit further ahead in terms of page numbers, but still called exercise 12H, so hopefully you don't have too much hassle finding those questions. Again, have a go at them, check solutions at the back and get in touch if you have any problems.